Hi, welcome to 2.6 Combinations of Transformations. In this video, we're going to look at combining all the different types of transformations that we have learned so far. So our reflections, our stretches, compressions, and our horizontal and vertical shifts. So we'll be combining all those at once. Our success criteria, I can describe the transformations applied to a function in both words and function notation, minding the proper order. So the order of the transformations is really important, especially when you're describing the transformation in words. We want to make sure we list them in the proper order. I can graph a transform function by applying the appropriate transformations to the base function. So we're going to use something called point mapping. What we'll do is we'll actually do all the transformations at once. So we'll take a base graph and we'll put it through the point mapping formula and we'll obtain our transformed function that way. Then we want to reduce the number of transformations required by algebraically simplifying the transformed equation. So yes, you can do that. If you get a really complicated transformed function, you can go ahead and algebraically simplify it. This will reduce the amount of transformations needed. So we'll see that a little bit later on in the next video. And then lastly, state domain and range for a transformed function. Okay, so here we have a function g of x. Okay, there's the equation. Okay, and in order to get this function, we've actually taken a base function, f of x equal to x squared, and we've applied some transformations to it. So by applying transformations to f of x, we can obtain this function right here, g of x. So I'm going to go ahead and I'm going to write that out. So right in here, what I'm going to do is I'm going to describe g of x as a bunch of transformations that happen to f of x. Okay, when I do that, that function will actually represent this equation here. Okay. So let's get this started. So in order to get this equation, I'm going to have to take f of x and I'm going to first have to multiply it by 2. So I'm going to have 2 times f. And now here I'm going to do a square bracket, okay? Now, the reason why I'm doing that is because my x that I have here has to switch to x minus 1, okay? So I'll have x minus 1, close it up, squared, okay? And then I can see here the next thing to do is to just add 1, so I'd have plus 1, okay? So what this does is this actually describes the transformations in function notation. This tells me all the transformations that I need to do to f of x in order to get there. Okay. All right, so I'm just going to write here, this is function notation. Okay, that's one way to describe transformations. The other way is to state them in words, the transformations. So we'll do that next here. So I can see that my a value for this is 2. Okay, so that's my number in front here, or this one right here. That's my value of a. And this just tells me that we're going to have a vertical stretch by factor 2. I'm going to go over the rules for all of these in just a second. So vertical stretch by factor 2, that's because my a is greater than 1. Okay, so this is my a value. Next I have in there is d. D is equal to 1. So this means we're going to have to shift to the right. Shift right 1 unit. Okay, and lastly, the plus 1 at the end, that's my value for c. So then that just means we have to shift up 1 unit. So those are my transformations described in words. And I also listed these in the proper order. So when doing these transformations, if you're going to do them one at a time, you would want to do the stretch first. Then you can do the 2 shifts last, okay? So it doesn't matter if you do horizontal stuff before you do vertical stuff. What matters is that you do the shifts last. Why do you have to do them last? Well, shifts always refer to like an addition or subtraction that needs to be made. So the graph goes up 1 unit, so we add one, or it goes to the right 3, so we add 3. The stretches and compressions always refer to multiplying the x values or the y values by something. So we always want to multiply follow bed mass before we do any adding or subtracting. So it just says note, we'll say here shifts should always be done last, okay? It doesn't matter what happens before that, just say the shift for last. Okay, so here is our general form for a transformed function. It's always going to look something like this here, where f is just some base function, okay? So here's all the different transformations, a, k, d, and c. And what I've done here is I've just wrote them out. We're just going to summarize all the different rules. So all you have to do is take this and then compare it to all the other equations later, and you'll know exactly what to do to get the transformed function or graph. So, all right, so A, there's a few things with A. First thing we want to do is we want to see if A is less than 0. Okay, if A is less than 0, that means it's negative. That means we're going to have a reflection along the x-axis. Okay. Then we want to look at the absolute value of A. Okay, so this symbol here, those two lines I wrote, it refers to the absolute value. Okay, what that means is just to take the positive value. Okay, that's all it means. So it basically means drop the negative. So because remember, if A is less than 0, that means A is negative. So first we're going to have the reflection, and then depending on the value of A, we may have a stretch or compression. So if the absolute value is greater than 1, then we're going to have a vertical stretch by factor A. Now, if A happens to be small and it's between 0 and 1, the absolute value, if it's between 0 and 1, like a half or 2/3, that's when we're going to have a vertical compression by factor A. Okay, what this does is it'll take any base point and it'll multiply the y value by A, giving us the vertical stretch or compression. Okay, so that's the A value. The K value, which is always inside the function, inside that square block. Okay. Same thing with this one. If K is negative, then we're going to have a reflection, but it's going to be along the y-axis. Okay, and if the absolute value of K is bigger than 1, so if you drop the negative sign and you get something bigger than 1, then you're going to have a horizontal compression, because the factor is always going to be 1 over K. So if K is big, like 3 or 4, you're going to have 3 or 4 down there. So 1 divided by 3 or 4 gives you a small number. So whenever the factor is small, you want to use the word compression. Okay. Now, if K happens to be small and it's between 0 and 1, then we're going to have a horizontal stretch by factor 1 over K. So if you think about it, if K is small and you do 1 divided by a tiny number, well, you end up getting a bigger number out. So if this is large, this needs to be a stretch. All right, then we got the values for D right here. So if D is greater than 0, you're going to shift right. D units. And if d is less than 0, shift left d units. Okay. What this means is my points x, y are going to turn into x minus d comma y. Sorry, x plus d comma y. Okay, I just realized we're missing the one for k, right? So remember k is the horizontal stretch of compression. So that always takes my points x, y, the base points, and we divide by k. Okay, so if k is, let's say, positive 3, well, k would be bigger than 1. It would be a horizontal compression because the factor is 1 over 3. So we would be dividing x by 3 in that case. That would give me the horizontal compression of a third. Okay, we're almost done here. We're going to do the last one for C. C is greater than 0, shift up, C unit. C is less than 0, shift down, C unit. Okay, either way, we're taking our point x, y, and we're adding C to the y value. All right, so those are all the transformations. So hopefully that was a good refresher. And we'll then go ahead and apply these to some examples. And these examples here, I just want to see if you can identify A, K, D, and C, and then state the transformation. Okay? So what we can always do is we can always compare our equation to something of this form. And I'm going to keep it color-coded just to make this kind of as obvious as possible. Close that up, and then we got plus C at the end. So I'm always going to be comparing this to this nice formula right here that I've written out. So once we can pull A, K, D, and C out of there, out of the equation, the rest is really straightforward. So let's begin this one here. We'll describe the transformations, and then we're going to write out the equation later. Okay, so this here is just telling me what's happening to get g of x. So it just says I'm going to take f of x, I'm going to multiply it by 2, I'm going to replace x with 3x minus 4, and then we're going to add 1. So anyway, let's go ahead, let's state the transformation. So a is equal to negative 2. So that means two things are going to happen. The first is it's going to reflect along x-axis. Okay, I know that because it's negative. Okay. And the second thing it's going to do is the absolute value of a is 2. So 2 is greater than 1, so it's going to be a vertical stretch by factor 2. So that's it for A. Now for K. K is inside the function, so this will be horizontal. My K value is equal to 3. So this is going to be a horizontal compression by factor 1 over 3, because it's always 1 over K. Okay, notice this is a small number, that's why I use the word compression. Okay, D. So D is 4. We have x minus 4, so I know D is 4. That's easy, that just means it's going to shift right 4 units. And lastly, C is 1, so it's going to go up 1 unit. Okay, so that's all the transformations described in words. So using our function notation right here, I can actually come up with an equation for g of x, because right now this just says what to do to f of x to get g of x. But if we're told f of x is x squared, well, now let's actually get the equation for g of x. So let's do that here. So we know we have to multiply everything by 2. Now I have f, the square block, that everything that square block needs to go in for x. So then it's going to be squared, so I can just put that in here. We got x minus 4, close it up. That'll be squared. And then we have the plus 1 at the end, so we'll write plus 1. So this is my equation for g of x. I could actually put this in Desmos and graph it. This one I can't. This one, I mean, I can't directly put this into Desmos. I'd have to also say what f of x is too, right? So, okay, so this is the actual equation. This is the transformations in words, and if you can do that, then you can really do any of these other questions. So if you want to even pause the video at this point and do B and C, you can go ahead. I just would like you to stop at D, okay? Because D is in a little bit of a different form, so we'll have to be careful with D. But if you want to pause and try to do B and C, go right ahead. I'm just going to continue on with this. So let's grab this little formula here. We're going to copy it, and then we'll paste it to do our comparisons with. So, okay, I'm just going to move some of that over a bit. There we go. Okay, so I can see that A is a half. So A is between 0 and 1. That means we have the vertical compression. You can just write this for short form. Compression by factor 1 over 2. All right, moving on. K. K is negative a half. So what that means is we're going to have, it's negative a half. Let me write the negative in. So first, let's state the reflection. So it's going to reflect along y-axis. That means the x values will change. And the absolute value of k is equal to a positive a half. So that means that's between 0 and 1, right? So that tells us we're going to have a horizontal stretch by a factor 1 over k. So I can write it in the half because k is a half, or I can calculate that and I can just say 1 divided by half is 2. So it's by factor 2. So remember, my factor is greater than 1, so I have to use the word stretch here. Okay, you can see how this is all kind of coming together and making sense. D. D is equal to, if I compare this to this, I know that D must be negative 4. D is negative 4, I get the plus 4 in there, right? So D is negative 4. That means we're going to shift left 4 units. And at the very end, we can see C is negative 1. That means we shift down 1 unit. Okay, time to write out our equation. So here I can see what we need to do to the base function to get g of x. So if this is my base function, this basically means this whole square block has to go in for x underneath the root. So I'm going to have a big square root with that whole square block in it. This will all be inside the square root. And then these will be outside. Okay, so we'll have 1/2, and then the square root, negative a half, x plus 4. And then outside of that, we have minus 1. So that's it. That's my equation for g of x. Okay, let's do this next one. So I'm going to copy that. Okay, there's my comparison. So I can see a is equal to negative square root of 3. So because it's negative, we're going to first reflect along x-axis. And then the absolute value of a is equal to root 3. Okay, we just drop the negative sign. Root 3 I know is bigger than 1. it is about 1.7. So that means it's going to be a vertical stretch. By factor, just write root 3. Okay, don't put in approximation. We want the exact value. So root 3. So that's that. Let's go move on to k. K is 0.2. So because k is between 0 and 1, we're going to have a horizontal stretch. By factor, it's always going to be 1 over k, so 1 divided by 0.2, which is just 5. So by factor 5. And d, in this case, is 2. Okay, it's always the opposite of what you see in there. So that means we shift right 2 units. And then c is plus 2. So then we'll just shift up 2 units. Okay, and now for my equation for g of x. So it tells me to do all this stuff to this base function. My base function is just x, okay? So what I'm going to do is I'm going to grab this square block, everything that's in it, I'm going to replace it inside of x, okay? And then on the outside, I'm going to multiply by negative root 3 and add 2, okay? So let's begin. We will have negative root 3, now times my substitution. So that whole square block is going to go inside here. And then I have plus 2 on the outside. So you can leave these parentheses as large, right? Or you can write them, you could write them as the square. It's the same thing, okay? But that's what was basically substituted in for x. Okay, now I would say you could clean this up a bit. Like you could distribute these in, and then you could distribute this in. But we have a radical here, and then times a decimal. It's just going to get ugly, and I want to leave things as exact. So I'm just going to leave this the way how it is. Okay. So I could type this right into Desmos and get the exact graph that I need. That would basically take this linear function and do all these transformations to it. Okay, so now moving on to D. So this one I said to be careful, right? I kind of told you guys if you're going to pause the video to stop here. Okay. So notice, I'm just going to put this here for now. Notice this isn't in this form. Okay, it's really close. Like I can see A, I can see K, I can see C, but notice this actually isn't D. Okay, it's not D because K always needs to be factored out from X. Okay, so in this expression in here, there should be another set of brackets. So in order to do that, we have to factor out the 3. That way, we're actually going to have the right value for D. So I'm going to leave this here. So this needs to be put into this form first. 2 times F. Now we're going to factor the 3 out. So I'm going to set up some round brackets and I'd have X minus 2. Close up the brackets, then plus 1. So you can see I factored 3 out from that expression. So 3x divided by 3 is x, and then negative 6 divided by 3, the negative 6 is 2, negative 2. Okay, notice if I multiply this in, I kind of have this up here, right? So K always needs to be factored out like you can see here. So now everything kind of lines up perfectly. So I always suggest you rewrite these out. When you see K not factored, rewrite it out. That way you don't make any mistakes because everything's the same here except for D. Notice my D is 2 instead of 6. All the other values stay the same. So if you forget to factor 3 out, everything on your graph is going to be correct except for the horizontal shift. You're probably going to end up shifting it too much. Okay, I need to move this over just to get a little bit of space. So I'm just going to put it right here. And A is equal to 2. So we're going to have a vertical stretch by factor 2. K is 3. So we're going to have a horizontal compression by factor, it's always 1 over K. So K is 3, so it's going to be a third. Okay, whenever you have a small number here, you always want to be using the word compression with it. My value for D is 2, not 6. So this is going to shift right 2 units. And lastly, C is 1, so shift up 1. Okay, now my equation. So I want to get the equation for g of x. So I can see what I have to do to f of x. This is my base here. I got to do all these things to it. So what I'm first going to do is I see that I have to multiply by 2 first by f. So I'm going to write 2. And then this whole square bracket, this whole block needs to go in for x. Notice x is on the bottom. So I'll show that substitution here. I can either write 3x minus 6, or I can write this block here, 3x minus 2, in factored form. So I'm just going to leave it in this form for now. So 3x minus 6. Okay, close up the brackets. And then we have to have a plus 1 at the end, so then I'll have plus 1. Okay. Now I want to clean this up. I'm just going to take this 2 and I'm going to multiply it, right? Because it's kind of like a fraction. I can just do 2 times 1. So I would have 2 over 3x minus 6 plus 1. So notice this doesn't change anything like by multiplying that in. I didn't eliminate a transformation, but I just put it in a nicer form that you could put into Desmos if you needed to. Okay, so that is basically every kind of scenario you can get. We did all the different base functions in this example, so we now know how to handle what they look like, and hopefully you can look at your function notation and pull out all your parameters, A, K, D, and C. When you're stating them, make sure you save the shifts for last. So an easy way to remember is just kind of go left to right as you go through, and you'll always save your shifts for at the end. Okay. All right, that's it for this video. I will see you guys in the next one.